Hi guys, so in the last class we were doing the questions of optical isomerism where we were trying to find out in which molecule there is POS or COS and whether the molecules are optically active or not. Okay, so now we were left with few more questions, so let's quickly finish them off and uh, and then we will get a better idea how to check the chirality or optical activity in a molecule. So I have written some questions over here. You guys pause the video, try these questions on your own, and then I'll discuss the answers. Okay, so let's begin with the first question now. We have to figure out whether the chiral centers are present or not. So chiral centers are not present because two same groups are present on each carbon. So no chiral centers. POS, yes, POS is there in this molecule. You can, but this is a planar molecule. So you cut it like this or you cut it like this. POS is present. When you talk about COS, does the COS present in this molecule? COS is present because this is a planar molecule. This is the center. If you draw a line through the center, it will go and meet this chlorine. Similar way, you will draw a line from this chlorine which will pass through the center and will meet this chlorine. So basically, this is something like this. So this is planar. Okay. So if I'll draw a line from the center, it will go and meet another chlorine over here. Similarly, I'll draw a line, it is like this here. I'll draw a line and it will go and it will meet over here. Okay, so this is a planar molecule and hence the COS is present. Chirality, no. Optical activity, no. Come to the next compound. In the next compound, what we have? We have chlorines, two chlorines on cyclohexane, not cyclohexane, cyclohexadiene, and then two chlorines which are present with those double bonds. So basically these chlorines are in the same plane as the double bond and the cycle, right? These two chlorines are above the plane, are basically, this is the ring, if let's say this is the ring, okay, and here is the chlorine somewhere, these two chlorines, okay, but these chlorines are towards the viewer like this, okay. So now we have to see whether the chiral centers are there or not. I think chiral centers are there. If you yeah, so this carbon and this carbon is a chiral center, so we have two chiral centers. We have to check whether the plane of symmetry is there or not. So when you talk about the plane of symmetry, cut it like this, will you get a plane of symmetry? No. You cut like this, you cut like this from the two chlorines which are towards the viewer. So definitely the chlorines will get the slice cut, half here, half here, half here, half here. But but are we forming the mirror image of this chlorine at this side? I mean, mirror image is supposed to be this side. Here should be the mirror image. But are we getting it? No. For this chlorine, here should be the mirror image. Are we getting it? No. So no POS. Okay. So no POS. Exactly same way. Both the chlorines which are opposite to each other are these wedge chlorines. Okay. Wedge chlorines are there. Basically both are towards the viewer. So if you'll pass a line through one chlorine and if you'll go to the next side, you're not getting any other chlorine in the opposite direction. So no COS. I just told you to check wedge and dash structures, wedge and dash things whenever you get such COS thing. I mean, you don't have to check it from all the ways, even if one differs, even if one is not following COS, or even if one is not getting its same equal and same group in equal and opposite direction, then the COS is not present. So here in this case, we don't have COS because chlorines are in the same, you can say are both are towards the viewer, and if you'll pass a line between these two chlorines, these lines are not passing through the center, and if you'll pass line through the center, you will not get the chlorine on the other side. So no COS. Chirality, yes. Optical activity, yes. Let's talk about the next compound. In next compound, do we have chiral centers? Yes, the molecule is same. Do we have POS? No. Again, POS is not there. It's the same structure as the previous one. So no POS. Okay. Then I think I'll just clear up the above one because there is a lot of mess around it, and I'll rewrite the answer. POS is there, COS is there, chirality is not there, optical activity is not there. Chiral centers are there, POS is not there, COS is not there, chirality is there, optical activity is there. Okay, now let's talk about the third question. In third question, again, we have chiral centers, we don't have POS. Why we don't have POS? Because we can't, because when we'll cut it into half, we are not getting the mirror image on the other side. So we don't have that mirror image on the other side, hence no POS. Do we have COS? Yes, this is the center. If I pass a line from the center, I'm getting a chlorine over here. This is the center. If I'll pass a line from this chlorine, I'm getting chlorine on the other side. It is like this. One is the chlorine towards the viewer, one is away from the viewer. You'll pass the line through it from the center. I mean, you'll pass a line from the center. It will go and meet another chlorine. So basically, on the equal and opposite direction, you have chlorine over here. This carbon has the same carbon over here. So basically all the groups are at equal and opposite direction. So COS does exist, and because of the COS, chirality is not there and optical activity is not there. Okay, so this is about these 3 questions, and let's try out few more questions on our own. Now again, try out these 3 questions, pause the video, and then I'll discuss the answers. So let's talk about the next compound. So we have this structure. This structure has 4 chlorines. All the 4 chlorines are towards the viewer, and then there is a double bond in the center. Now if I have to figure out whether the chiral centers are there or not, there are chiral centers 1, 2, 3 and 4. These are the chiral centers. So we have chiral centers in this. Do we have POS? Let's see. If I cut it through this plane, am I getting equal? Am I getting the mirror image? Yes, I'm getting the mirror image. So POS is there. Do we have COS? For COS, the line should pass through the center and you should get the same group in the opposite direction and same distance. So just imagine all the 4 chlorines are wedges. Okay, so basically all are towards the viewer. So if you will try to match one chlorine and then you will pass a line through the center and try to find out the another chlorine on the other side, are you getting it? No, because the chlorines are all on the top like this. Okay, so we will not be able to get any chlorine in the opposite direction. If I'll pass a line, it looks like there is a COS because this looks like it is in the opposite direction, but no, just understand this is a wedge shape, means all are towards the viewer, all are standing in the same side. So basically it's like this. I mean, obviously not right example, but let assume this is chlorine 1, 2, 3, 4. All the chlorines are towards the viewer. So when you will try to draw a line between one chlorine and another chlorine, that is not passing through the center, and if you pass a line through the center, you're not getting chlorine on the opposite direction. So no COS. Chirality, no. Optical activity, no. Okay. Now similarly in the next compound we will see, do we have chiral centers? Yes, the molecule is same, so chiral centers are there. Do we have POS? If I cut it like this through this plane, we are getting POS. Okay, not through the horizontal plane, through the vertical plane. Now we have to see whether we have COS or not. Now if I'll pass a line through the center, which is connecting this chlorine and the other chlorine over here. Now what is the case? One chlorine is up, one chlorine is down, and the line is passing through the center. COS is there. Same is the case for this chlorine. Same is the case for this carbon. This carbon is if I'll pass a line from this carbon and which will pass through the center, it will go and match this carbon. Exactly same way, if I'll draw a line from this carbon and make it pass through the center, it will go and match this carbon. So every single point or every single carbon and chlorine is matching, or you can say you can find in the equal and opposite direction when the line passes through the center. So COS is present in this case. Chirality, no. Optical activity, no. Now let's talk about the third case. In third case, or in the 6th question, do we have chirality? Do we have chiral carbons? No, we don't have chiral carbons because the molecule is symmetric. So neither this nor this nor this, none of the carbons are chiral. Do we have POS? Yes, we have. You can cut it through this plane. Half chlorine will go this way, half chlorine will this go away, and these two are mirror images of each other. So yes, POS is there. Do we have COS? No, we don't have COS because if I'll draw a line, this chlorine is not getting any opposite chlorine over here, this chlorine is not getting any opposite chlorine over here, this chlorine is not getting any opposite chlorine over here. So no COS. Chirality, no. Optical activity, no. So I hope you guys are getting it. I am getting little faster. If you are getting stuck at any of the example, you better ask me in the doubts class because it is very, very important. This part especially is very important. Okay, I'll just clear up this mess so that you can note it down, and I'll rewrite or I'll refill the whole table. So this is your chirality, yes. POS, yes. COS, no. Chirality, no. Optical activity, no. Chiral centers, yes. PUS, yes. CUS, yes. Chirality, no. Optical activity, no. Chiral centers, no. PUS, yes. CUS, no. Chirality, no. Optical activity. So you can note it down now. Okay. Now I'll move to the next set of questions. Again, try them out on your own and then we'll discuss the answers. Now here are the questions. Note them down, pause the video, try them out on your own, and then I will discuss the explanation of these examples. Okay, so let's start with the first structure now. So in this structure, what we have to figure out whether we have chiral centers or not. It is the same as the previous example. So there were no chiral centers in that. Here also there are no chiral centers. We have PUS. Yes, we do have PUS. If I cut it through this plane, half chlorine will go this way, half chlorine will this go way, and these two chlorines are mirror images. This chlorine and this chlorine is mirror image of each other. So PUS is there. CUS is not there in the system because we don't have the same groups in the opposite direction. So there is no need to even mark the line in the center. You can clearly see this chlorine doesn't have anything in the opposite direction. So no COS, no chirality, no optical activity. Now next question. In the next question, these are cumulines. If you remember, we have done this in geometrical isomerism, and I told you the structure how cumuline works. So let's see first how the things are. So basically, I'll draw the plane with a different color. So basically, this carbon is forming a pi bond over here. Okay, right? And your H and CH3 will be in the perpendicular plane to it. So H and CH3, right? Now, when I'm talking about this pi bond, then this pi bond will form in the opposite plane, or you can say perpendicular plane. So this is my pi bond, and then this H and CH3 will be in this plane. This H and CH3 and this H and CH3 are in different planes. This we have already discussed. I am not getting into depth of it because we have done it in much more detail in case of in case of geometrical isomerism. I can just show it over here to you. So assume this is the structure of cumuline. I have not shown the pi bonds or anything. Rest of the center things are all in the same plane. And then this is how the structure is. So basically these are in the plane, these are in one plane and these H and CH3s are in the different plane. That's how exactly your cumuline looks like, right? Don't bother about this yellow color. All these three are carbon. So I was not able to find the same color atom or ball. So that's the reason why I have put yellow over here. But these are all connected to the pi bond, and these are the sigma bonds over here. So one is in the in this plane and another is in this plane. So these are in the plane perpendicular to each other, right? So these two groups are in different planes with respect to each other. Now we have to see whether the chiral centers are there or not, or PUS is there or not, or CUS is there or not. So let's see whether chiral centers are there. Chiral centers are not there in this compound. Okay. Now we have to see PUS is there. Just look at this molecule. If I do this slice cut like this, am I getting a PUS? If I cut it like this ball will go here, ball will go here, this hydrogen will go here, this hydrogen will go here. But here, are we getting the mirror image? If I'll cut it like this, am I getting a mirror image? No, here is a hydrogen and here is CH3. So I'm not getting the mirror image over here. If I cut it like this, am I getting a mirror image? No. If I cut like this, am I getting the mirror image? No. Again, here is a CH3 and here is hydrogen. If I'll cut, one part will get CH3 and another part will get hydrogen. These two things will get cut into the slice cut form, but this part will not have the mirror image. So by any way am I getting PUS in this molecule? Is there a way to get a PUS in this molecule? I don't think so. You think on your own and tell me, or you think and tell me if I'm telling anything wrong. So neither you can cut it vertically, nor you can cut it like this, nor you can cut it like this. So anyway, you cannot get a PUS here. So no PUS here. Okay. Do we have any center of symmetry? If I pass a line through the center, am I getting a same group in the opposite direction? No, it is very clearly visible that we don't have the same groups in the opposite direction when a line passes through the center. So no CUS. Chirality, yes. Optical activity, yes. So see, in this compound, you can clearly see neither we have chiral centers and PUS, CUS both are absent, and still chirality and optical activity is there. So as I mentioned earlier also, chiral centers presence is no is no criteria for any compound to be optically active. Now let's talk about the next compound. So this is my next compound. In this compound, what we have, one end both are hydrogens, and in one end we have CH3 and one hydrogen, and then there is the carbon chain in the center. Now we have to see whether we have chiral centers or not. We don't have chiral centers. We have POS or not. If I cut it like this, like this, what will happen? One hydrogen will be up, one hydrogen will be down. Then all these carbons will get cut through the center. Then CH3 this CH3 will get cut into half up, half down. This hydrogen will also get half up, half down. So when I'll cut it, this part will be mirror image of this, and these halves will be mirror images of each other. So yes, it possesses POS. Why? Because these two atoms were same. If these two atoms or these two groups wouldn't be same, in that case it wouldn't have possessed POS as in the last case. So here you can cut it like this horizontally, and then these groups will get divided into half in two halves, and then this is the mirror image of this. Okay, so POS is there. Yes, POS is there. I hope you can see what is the molecule, what molecule I'm talking about, how does it look like. If it is not clear to you, you can just see it again. Okay, now we have to figure out where this is plane of symmetry is present. Yes, plane of symmetry is present. Is COS present? So no, COS is again not present, because I cannot get the CH3 in the equal and opposite direction if I pass a line through the center. Same is the case for everything basically. It's not only about CH3 but everything. You won't get the same group in the equal and opposite direction. So it is very clearly visible. So center of symmetry is there? No. Chirality is there? No. Optical activity is there? Okay. So this is about these three structures. Let's see few more. So again, I have written few structures over here. Try them out on your own, and then I'll discuss the answers. Okay, so let's try out these ones. So the first compound, what I have mentioned over here, this compound is nothing else but the same compound as this. I've written it twice so that you can see it clearly that there are two hydrogens. Now when you're talking about these two cyclic chains connected to each other, these two cyclic chains are not planar with respect to each other. So one is in one plane. So if you can see it over here, one is in one plane and another is in the different plane. So they are in the perpendicular planes to each other. How? Why? We have already discussed this in geometrical isomerism. And the bonds which they are forming over here, these are also this bond will be in the opposite plane with respect to the ring, and this bond will be in the opposite, not opposite exactly, perpendicular plane. Not the opposite is the wrong word. So these bonds will be in the perpendicular plane with respect to this chain. These bonds will be in the perpendicular plane with respect to this ring. Now, if you want to actually visualize, think on your own that why it has happened, and as I will show you the molecule over here. So this is how my ring looks like. This is what exactly I am forming over there also. So one ring is in one plane and its sigma bonds over here are in the perpendicular plane. So this is my ring, this is my first ring, and these are the bonds in perpendicular, or you can say the sigma bonds in perpendicular. Then comes the another ring. This another ring is again in the perpendicular plane, and these bonds, these sigma bonds, are in the same plane as the previous ring. This is what exactly I have shown you over here also, and I had shown the plane with the different colors. So basically yellow is one plane and blue is another plane. So this is blue plane thing, this is blue plane thing, this is yellow plane thing, and this is yellow plane thing. So the cyclic ring and these bonds are in the same plane, and this cyclic ring and these bonds are in the same plane. So now in this we have to figure out whether the chiral centers present are there or not, POS is there or not, COS is there or not, chirality is there or not. So do we have any chiral centers here? This carbon, hydrogen and CH3 is connected, but rest of the chains are symmetric, so no chiral center. Rest of the other places doesn't even look like that they can be chiral center. Now let's talk about POS. So do we have POS over here? If I just look at it very, very carefully, if I cut it like this, if I do the vertical cut, this will get divided into two equal halves, this will get divided into two equal halves, this cycle will get divided into two halves, this will get slice cut, and what will happen to this? What will happen to this? One hydrogen will come here and one hydrogen will go there. So if I'll cut it vertically, then these two things will break into two equal halves, one this side, one this side. This chain will cut into one half here, one half there. These carbons will cut into equal halves, half this side, half this side, and this hydrogen will go one this side, one this side. So does this possess POS? Yes, it does possess POS. But do we have COS over here? Do we have center of symmetry over here? Can we see if I pass a line through the center, I am getting the equal and opposite group over there on the opposite direction? No, I am not. Just check for one and you're not getting it. COS is not there, chirality not there, optical activity is not there. Now, if I change my molecule a bit and I make it, let's say, I'll just add one more compound over here. So assume I'm making change here itself. Okay, let me just correct it. So I'll put cut, yes, no, no, and no over here, and I'll change this molecule a bit. Okay, so in this molecule I'll place one CH3. So you'll have two different compounds. Now in the second molecule, I have made a change in the molecule, and what we have done is, rather than two hydrogens on one side, we have one CH3 and one hydrogen. Now if I put one CH3 here, okay, now tell me, do we have chiral centers first of all? So we have to check whether we have chiral centers here. No, we don't have chiral centers here. Do we have POS? Let's see. So here is my molecule and we have to figure out whether we have POS or not. Let's try out the exact same way how in the previous question we did. We will cut it like this. If we'll cut it like this, we'll get hydrogen at one side and CH3 at one side. In the earlier case, it was both hydrogens. So everywhere else it will be cutting and giving the mirror image, but at this point of time it will start differing. Okay, so this cannot give POS vertically. Let's cut it horizontally. If I cut it like this, again at this point, this hydrogen and CH3 are not mirror images of each other. If I'll cut it like this, one half will get one hydrogen, another half will get CH3, right? So this does not possess POS. No POS. Do we have COS? No, we don't have COS. CH3, if you pass a line through the center, are you getting the CH3 in the opposite direction? If you pass a line through the center, are you getting the CH3 for this in the opposite direction? No. So no COS. Chirality, yes. Optical activity, yes. So this molecule is chiral. Now look at another one. I'm not going to show you any more 3D pictures. So you visualize on your own and try out this one. So do we have chiral centers over here? Chiral center in this, yes, we have. This carbon is the chiral center. Even this carbon is the chiral center. So yes, we have chiral centers over here. How? I'm not going to teach you the chiral centers right now. You already know how to find out chiral centers. Think and visualize, think and open the chain and you'll get it. Now we have to check whether we have POS or not. If I'll cut it through this plane, am I getting the mirror image? No. Why? Because up is CH3 and down is, up is hydrogen, another is CH3, so I'm not getting it. So if I cut, if I do the vertical cut like this, am I getting the mirror image? No. Why? Because one part will have CH3, another part has no CH3. So this side we don't have CH3. So even if I'll cut it like this, everything will get divided into two equal halves, but the CH3 is not present in the other side, and hence we won't get POS. Just see it over here, just in case if you're not able to visualize. So if I'll cut it like this, everything else, this should have been hydrogen, my bad. So if I'll cut it like this, one side will get CH3, another side doesn't have a CH3, and hence no POS. Do we have COS? No. Very clearly no. Chirality, yes. Optical activity, yes. Now look at this compound. In this compound, what we have hydrogens. So very ideal condition for POS. But will this possess POS? I don't think so. This will possess POS. Why? Because we don't have chlorine in the opposite side. So we don't have chlorine this side. So if we'll try to do this cut, the vertical cut, we won't get the mirror images. If I'll cut it like this, then also I will not get the mirror images. If I'll cut like this, then also I'll not get mirror images. So either way, I'm not going to get mirror images due to the presence of a chlorine over here. Do we have chiral centers? Yes, we do have. This carbon where the chlorine is present is the chiral center. So chiral center is there. POS is not there, COS is not there, chirality is there, optical activity is there. Okay. So here we are done with these questions also. Let's try out few more remaining questions. The cases which we've already seen in geometrical isomerism, the same cases I'm repeating in optical to figure out whether optical activity is present in these compounds or not. So let's see the next few examples. So now let's discuss. We have already spoken about the alkylamines in case cycloalkylamines in case of in the previous chapter in the previous geometrical isomerism, and then what we have told you is that whichever plane this cycle is, your these sigma bonds will be in the perpendicular plane. So if this is in the plane of the, let's say, board, if this is standing like this, your these H and CH3 bonds will be it's like this. Okay. Let me not complicate it much. Let me show you this. So if this is your cycle, or let's write it like this. If this is your cyclic ring, okay, then these bonds are in the perpendicular plane like this. Then there is a pi bond, then there is a carbon, and then again these two bonds are in the perpendicular plane, right? So that's how it is, and these two will be in the different plane altogether. This we have already discussed. I mean, this I'm not going into much depth and much detail because we have done a lot of cases for the same, and at that time I had explained you how exactly you have to figure out the plane and how exactly you have to figure out whether the groups have the same plane or the different plane. So this will be, these two bonds will be in the same plane as the pi bond, and these two bonds will be in the same plane as the plane of the cyclic ring. Okay, so this is how it is. The first group, even if you had not understood in the geometrical isomerism, at least now you can visualize it much better. Please try to visualize. See. Okay. Now I have to figure out whether the chiral centers are there or not. For the first case, the chiral center, I'll check it for this carbon, but both of the sides are same, so chiral centers are not there. POS is there or not? How will we check? We will try to cut it through the different planes. So I can cut it like this. If I'll cut it like this, everything else will get divided into two equal halves, but here we will get CH and hydrogen which are different from each other. So like a vertical cut, you cannot get the mirror image. Let's see the horizontal cut. Can you do the horizontal cut? I can do the horizontal cut. Here again we will get two equal halves, but here we will get one half will get hydrogen, another half will get CH3. So this way also we cannot cut it into two equal halves and mirror images. So POS is not there. Is COS there? Can we, if I pass a line through the center, if I pass a line through the center which touches the CH3, am I getting a CH3 in the opposite direction? No, I am not. I am not getting CH3 in the opposite plane, equal and opposite direction, so no COS. Same is the case here. If you pass a line through the center, are you getting the CH3 in the opposite side, equal and opposite direction? No. So no COS, chirality yes, optical activity yes. Now look at the another structure. In the another structure, the difference what we have made is, now instead of the CH3 we have a hydrogen over here. So let me just put the hydrogen here. This is my hydrogen. Now this is my structure, and again chiral centers are yet not there. POS is there or not, that we have to check. Now we can cut it through this plane, okay, through this plane. So what will happen? One hydrogen will go up, one hydrogen will go down. This carbon will get divided into two equal halves. This carbon will get divided into two equal halves. This cycle will get divided into two equal halves. And then what about these two? CH3 will get divided into two equal halves up and down, and this hydrogen will also get divided into two equal halves up and down. Okay, so basically everything will get divided into two equal halves and will form the mirror image. So yes, POS is there. COS is still not there, chirality is not there, optical activity is not there. Now last two questions for practice. These are ortho substituted benzenes, tetra ortho substituted benzenes. Let's see how to check the chirality in these cases. So now we are talking about the tetra substituted dibenzene, ortho, tetra substituted dibenzene. We have already discussed these cases when we were doing the geometrical isomerism, but today I'll be showing you the actual 3D model of these molecules so that you can visualize better. And now once you'll visualize, once you'll get to know how the model looks like, every time when you'll get such question, you'll be able to do it very easily. Okay, so first of all, we'll see whether the chiral center is present or not. Chiral center is not present in this molecule, and even in the down molecule, no chiral centers. Now we have to see whether the plane of symmetry is there or not. For that, we have to see, you have to understand when you're talking about two benzenes connected to each other, one will be in one plane and other will be in the perpendicular plane. So these are two benzene rings connected to each other in the perpendicular plane with respect to each other. So how will it exactly look like? This is how exactly it will look like. I hope you guys can see this. This is one benzene ring. Here on the top, yellow color ball is COS, the down gray color ball is NO2. Here is your NO2 and here at the back is your COH. So this is how they are in the perpendicular plane with respect to each other, two benzene rings. Okay, now we have to see whether we have POS and COS in this molecule or not. So if I try to cut it you can say vertically, then what will happen? Every ball in this ring will cut into two equal halves and get divided into two equal halves. But what about this? If I'll cut this ring, what will happen? One half will get NO2 and another half will get COH. So not forming the mirror image of each other. Same way, if I'll cut it horizontally, every ball or every atom of this ring will get divided into two equal halves. But what about this ring? This ring will get split from the center. First half will have COH and second half will have NO2. Again, no mirror image, no equal halves. So is POS existing in this molecule? No. No POS. Cut it. Now you yourself see and tell me whether COS is there or not. Are we getting the COH in the equal and opposite direction when the line passes through the center? No. Are we getting this NO2 in equal and opposite direction when the line passes through the center? No. So no COS. Chirality, yes. Optical activity, yes. Now in the another molecule, there is a small change what we have made, and that is in the first benzene we have put both the COH, whereas in the second benzene we have put both the NO2s. What I'm doing right now, I'm just fixing my benzene thing so that I can show you how the next molecule looks like. So this is how our next molecule looks like. Now in this, two COH are there in one ring and two NO2s are in the another ring. Now we have to see whether POS exists or not. If I cut my ring horizontally like this, what will happen? These two balls will get divided into two equal, every ball in this ring will get divided into two equal halves, one up and one down. Similarly, this ring will also get divided into two equal halves, and now these halves have the same group, COH, COH, right? Even if I cut it vertically, what will happen? This ring will get divided into two equal halves, which are mirror images of each other, and this ring will also get divided into two equal halves. One half will have this NO2, one half will have this NO2, and hence will be forming mirror image of each other. So no matter you cut it vertically or you cut it horizontally, you will get two equal halves which are mirror images of each other. So does this molecule possess POS? Yes, this molecule possess POS. But what about COS? COS is still not there. You don't have the COH in equal and opposite direction when the line passes through the center. Same is the case for this. These are here. NO2s are here, COH are here. These are when you connect the line between this COH and this COH. Is this line passing through the center? No. So no COS in this molecule, but POS is there. Okay. So POS yes, COS no, chirality no, optical activity. So here we are done with all the possible different examples what we can get in the exams, and most of the examples I have tried showing you through the 3D diagram so that you can once see and then you can visualize it from the next time. Now we will write some important points, some important things what about whatever we have learnt, as in like what all different structures we have learned, cycloalkalidenes and cumulines and these benzene thing, in which all cases the optical activity will exist. So let's note it down. Okay, so what's the key point? Key point is even cumulines and even spirines and even cycloalkalidenes, we have taken the example before, can show optical activity. Odd ones will not show. Even ones can show when the terminal carbons have two different groups attached to it. So let's say hydrogen CH3, hydrogen CH3, and like that. So two different groups, if they are attached on the terminal carbons, then only they will show optical activity. If the two different groups are not present there, then at least POS or COS will be present. COS will not be, but POS will be present, and in that case they will not show the optical activity. So you don't have to every time visualize also. You can just remember this rule, and whenever you'll get a question, if you'll see even cumulines over there, even spirines over there, even cycloalkalidenes over there, just look at the terminal carbons positioning and the attachments over there, and then you can decide whether the compound will give you optical activity or not. So here we are done with the examples where we had to show different compounds can show optical activity or not, what are the bases to check them. Next we will be talking about Fischer projection. The next part is Wejen-Dash formula and Fischer projection and conversion of Wejen-Dash to Fischer projection.
So what is wedge dash formula? Wedge dash formula is a 3D representation of a molecule where we represent three types of lines to represent the view or three-dimensional structure. Two lines are the simple solid lines, whereas one is a proper thick bond, which is bold bond sort of thing, and other third one is the dash bond. So if you look at the structure, this is how the bonds are. Two are the plain bonds, and one bond is a dash bond and one bond is a wedge bond. This kind of bond is called as wedge. This kind of bond is called dash, and other two are normal lines. So two bonds are at the plane of the paper. Now look at this molecule. This molecule, I am keeping two bonds at the plane of paper. So this purple one and the gray one, if you can see this purple one and gray one, I am keeping it at the plane of the paper. So let's say this is the plane of the paper. Here I have kept. Okay, this is how I have kept at the plane of the paper. Now if you are a viewer, then you are able to see this yellow ball. This is towards you, so you are the viewer, towards you is the yellow ball, and then at the back end, at the back side, there is a blue ball. Yellow ball is towards you, purple and gray are at the plane of the paper, yellow one is towards you and blue one is away from you. So these are the four representations. These two balls are at one plane like this, then yellow one is towards the viewer and blue one is away from the viewer. Are you able to see this? And this thing is the center carbon. So that's exactly we are talking about. So this is how a 3D molecule is represented. Two bonds, we keep them at the same plane. One is towards the viewer, one is away from the viewer. Here the viewer is you, so yellow ball is towards you, so this is towards you, and this bond will be represented, the yellow ball and the bond will be represented by wedge representation. Wedge representation tells you about the bond which is coming towards the viewer, or which is directly in front of the eyes of the viewer. Whereas this blue ball, which is away from you, is represented by dash, dash. Okay, so this kind of representation, this dash representation, is basically used to denote that the bond is away from the viewer. So this is a 3D geometry. What we take, the solid lines, the normal solid lines, these lines, the normal solid lines are used to represent the bonds that are in the plane of the paper. As I mentioned, assume these are the four different groups and these two are in the plane of the paper. Okay, these two are lying in the plane of the paper. So this yellow one is towards you and blue one is away from you. So which one is towards you will be represented by wedge, and the one which is away from you will be represented by dash. So dash line to represent the bonds that extend away from the viewer, and wedge shaped lines are used to represent the bonds which are orienting facing the viewer. Okay, once more I'm telling you so that it will be easy for you to relate the stuff. Though we already have done this, we already know what is wedge and dash representation, but it is better to see it through the model. So these two are in the plane of the paper. Assume this is the paper. So these two, purple and gray, are in the plane of the paper. Yellow is towards you, blue is away from you. So yellow will be represented by wedge, blue will be represented by dash, and these two will be represented by normal solid line. So this is your wedge representation. Now let's talk about what is the Fisher projection formula. So now let's talk about the Fisher projection formula. We have seen what is wedge and dash. So that was also one kind of 3D representation of the molecule. Whereas when we talk about the Fisher projection, that is a 2D representation of the molecule. Okay, so when we say we have to convey some sort of information regarding how to draw a 3D structure on the plane of the paper, or how to draw a 3D structure on the paper, one way is using wedge dash, another way is using this Fisher projection. Apart from that, especially for the chiral compounds, we need to see whether the mirror images are superimposable or not, and whether these are optically active or not. So at that time we also check out for the configuration of the molecules. Configuration as in whether the orientation of a molecule is R or S. So all those representation, what does that means, that all we'll be talking about in the next few classes. So basically we will have to check some sort of configurational change which is happening in the mirror image of the compound, because of which the optical activity is changing. That also we have to check, and for checking that, when we talk about wedge dash, it becomes a little difficult to analyze and then to see and then imagine everything, visualize everything, and then put it in place. So the best way is to draw the Fisher projection or 2D representation of it, and then look for what all information we require. So as I mentioned, Fisher projection is especially for those compounds which are chiral. So we cannot draw the structures of Fisher projection which are not chiral. Okay, not chiral as in which do not contain chirality. Basically, the molecule must be chiral, and then only we can draw the Fisher projection. So Fisher projections tells us a lot of information about the stereochemical. It gives us a lot of stereochemical information. What do you mean by stereochemical information? A lot of information with respect to the orientation of the molecules as well as what configuration do they contain. For example, when you talk about alkenes, alkenes can be represented as cis and trans. Exactly same way, your optical compounds or optically active compounds also have isomers, and those are called as R isomer and S isomer, about which you will be studying later on. So those isomers can be ideally represented by the Fisher projection. So they tell us a lot of information without drawing the 3D structure, which can be very complicated for bigger molecules. These representations are used for the molecules that contain chirality. This is the mandatory condition, or chiral centers. If the chiral centers are not there, then we cannot draw the Fisher projection of the molecule. So we represent the molecule as this cross, and this cross, the center represents the chiral center or chiral carbon, and then the 4 attachments on it. So we can draw Fisher projection only when we get a wedge dash formula, and then we extract some information from there and then place it in the Fisher projection. So now let me just explain you how the wedge dash formula and Fisher projection is related. As I mentioned earlier, that when you talk about a wedge dash formula, 2 bonds are at the plane of the paper. One is towards the viewer and one is away from the viewer. So this is your wedge and the blue one is your dash, and this is the chiral center, and these 2 atoms are at the plane of the paper, right? That's how your molecule is. That's how your wedge dash representation is. To draw the Fisher projection or to draw the 2D representation of this molecule, what exactly you have to do? You have to move the one which is towards the viewer, you have to move that bond a bit, as in like the bond which you call it as wedge bond, you have to shift it in such a way that the molecule moves a bit, and then the both the bonds, one which was wedge and one which was dash, both comes towards the viewer. So now I think you can see the yellow ball as well as blue ball, which was not visible earlier. So now what we have done, this was the molecule structure earlier. This is how the molecule was when I was assuming that these 2 are in one plane, and then yellow one is towards the viewer and blue one is away from the viewer. Now to make the Fisher projection of it, what we do is we move or we tilt or we rotate the molecule a bit in such a way that now wedge and dash bonds both will come towards the viewer. These 2 are towards the viewer. You can see the blue ball as well as the yellow ball. So basically dash bond as well as wedge bond, both are visible to you, whereas the 2 bonds or the 2 molecules which were in the plane of the paper will go away from you. So this purple is away from you and this gray one, the down one, is away from you. So these 2, it's like this, it's like this. These are the 2 hands, and assume my body is tilted from the center. So it's like this is how the back bonds are which are away from the viewer, and this is how the front bonds are which are towards the viewer. So basically these two will be away from the viewer and these 2 will be towards the viewer when I rotate the molecule a bit. And now this molecule has to be written as in the Fisher projection. Now how will we write the Fisher projection of it? This center carbon is the chiral carbon, right? Now what we will do is the 2 bonds which are towards the viewer will be written in the horizontal line, of the Fisher projection, whereas the 2 bonds or whereas the 2 molecules which are away from the viewer will be written in the vertical line. Okay, so let's take an example. Let me just draw a wedge dash representation. So there is one compound here. I have written C, CHO, CH3, OH and hydrogen. So assume I am the viewer, What I am doing is, so this is my CHO, this is my CH3, this is my hydrogen, and this yellow thing is my OH, to which I am looking at. So I am looking at it. This is the plane of paper, all of you look at it, and for me, I am looking from here. So this yellow color ball is visible to me, this is directly towards me, and this hydrogen is away from me. All of you guys can see, right? These two are in the plane of paper. This OH, yellow ball is OH, which is towards me, and this hydrogen is away from me. That's what I have drawn. Now what will I do if I have to make the fissure? I will tilt it like this, right? Now these two bonds are away from me, and these two yellow and the blue bonds are towards me. So basically OH and hydrogen both are towards me, whereas CHO and CH3 are away from me. And when I have to draw this molecule in a 2D representation, how will I do it? I will write it like this. I will write it like this. I'll make a cross. This cross has a carbon in the center, and this is this chiral carbon, the black carbon, which I'm showing it over here. This black carbon is being represented by this cross. Now the two groups which are there away from me will be written on the vertical line. So I have the CHO and CH3, CHO and CH3 away from me. So I'll write CHO and CH3 on these vertical lines, whereas I will write these two groups which are towards me. So this yellow one, which is CHO, is on my left, and I will write it on left, OH. And the hydrogen, this hydrogen is on my right, so I'll write it on. How did we do it? Basically, I just moved this whole molecule like this, and I had made it like this. So my molecule now is OH, C, H, and at the back is your CHO, and at the back is your CH3. So these two bonds, this one and this one, is away from me, and I'm watching, or I'm looking at my molecule from here, and this side is OH and this side is hydrogen. So that's how we make the Fisher projection. But obviously for you initially it will be a little difficult to imagine and then write it. So we will go by some rules and just look at those rules and then draw the Fisher projection. So what I'm trying to tell you over here, the horizontal line represents the bonds which are coming towards the viewer, whereas the vertical line represents the bonds which are going away from the viewer. So here, what have we written? We have written the same thing. We are converting the 3D representation into 2D representation, where horizontal lines represent the bonds coming out of the plane of the paper, whereas vertical lines represent the bonds going behind the plane of the paper. So it's like these two are towards me, and let's say this is the plane of paper. Okay, this is the plane of paper. So these two are going behind the plane of the paper. This is the plane of the paper. This is what we were referring to, the plane of paper earlier, right? So plane of the paper still remain the same. This purple and gray ball are now behind the plane of the paper, whereas this yellow and blue are like out of the plane of the paper and towards the viewer. So that's how your horizontal line and vertical line representation will be. So let's understand in a little more detail, step by step, rule wise rule, okay, so that you get a better clarity how to convert a molecule of wedge-dash representation into the Fisher projection. So when you have to convert the Fisher projection, the wedge-dash representation to the Fisher projection, we will follow certain rules which will help you out in simplifying the whole process, which I have told you orally. I have taken an example of lactic acid over here, where CHO and CH3 are at the plane of the paper, whereas OH is towards the viewer and hydrogen is away from the viewer. So now we have to convert this lactic acid molecule to the Fisher projection, right? So first of all, the first step is what we will do, we will represent the chiral carbon. We will find out the chiral carbon. So this is my chiral carbon, and then the chiral carbon will be represented by cross. So I will write a cross. Look here, I will write a cross, and this center is representing the chiral center or chiral carbon. So there is nothing complicated till now. Go to the next step. In next step, what we will do, On the vertical line of the Fisher projection, place the groups which are shown by the normal bonds in a wedge dash formula. So these two bonds, CHO and CH3, have been represented by the normal bonds, right? So these bonds, whatever is attached on these bonds, put it on the vertical line. So I have COOH and I have CH3 on these normal bonds or normal bold bonds, and then that is what we have put it in the vertical line. Now we have to figure out what to put on the horizontal line. Okay, so the next rule says, that we have to now place the groups on the horizontal line, and there can be a little confusion that how to place the groups on the horizontal line. Till now we have done COH over here, CH3 over here. Now what we can see is OH is present over the wedge bond, whereas hydrogen is present over the dash bond. So I told you, whenever there is whenever the wedge bond is towards the viewer, when we are looking at certain compound, we'll just tilt it, bring both the wedge and dash towards ourselves or towards the viewer, and the bonds which were in the plane of the paper will go away from the viewer. So that was something I told you. What we are doing, this yellow ball is towards me, but to make the Fisher projection, first of all I'll tilt the molecule, I'll move it a bit, I'll rotate it a bit. Now my dash and wedge and dash, both bonds are towards me, and the simple bonds which were in the plane of the paper are away from me. So that movement we do. But how do we do this movement in the molecule which is written on the paper? Because I will not be carrying, or you will not be carrying, this 3D representation all the time. So what we do is we just move the OH a bit. If you can see over here, we have shifted the OH a bit and moved the OH in the opposite direction. We will never cross hydrogen. See, there are two things. One is OH can be moved this side, and another is OH can be moved the other side. Okay, OH can be moved this side, or OH can be moved on the green side, but we will never be crossing the dash line and then putting OH on the other side. Instead, we will be just moving the OH without changing, without shifting the hydrogen, without shifting the dash representation. We will just move our wedge representation in the opposite direction, and when we'll move it in the opposite direction, what will happen? This OH will come this side of CH3. So we don't have to touch hydrogen or the dash bond at all. What we have to do is we just have to, my bad, I have written CH3. We have to just move OH from its own place to the other place crossing the lower line or the lower normal straight bond. This is how it will become. It was closed like this earlier, and now it has got open like this. It was closed like this, the bond was a little closed like this, and now it has got open like this. That's what we have to do. Okay, we don't, if it is like this, I'm not going to cross my dash and put my bond other way around. That's not what I'm trying to do. What we are trying to do is, this is my wedge, this is my dash. I'm just moving the wedge like this. I'm opening the bond. Okay, when I'm opening the bond, I'm moving my OH from one place to another. I'm not touching my hydrogen at all. I'm not touching anything which is present on dash at all. Okay, so when I'll move this, it will get open like this. Now it becomes a little simple structure, and now I can place these molecules on, depending upon in which direction what molecule is. I'll just put it in the horizontal line. So OH is on the left, so I'll put it on left. Hydrogen is on right, so I'll put it on right. That's all we have to do. We have to just move our dash in the opposite direction, open the bond, and then place it with respect to their directions on the Fisher projection. Now, so is this part clear to everyone? I hope you have understood what we are trying to do. You will never do this mistake. You will never move the molecule in this way. Let me just show you what I'm talking about. This is COOH, this is CH3, this is hydrogen, and this is OH. I have seen people doing this kind of mistake, that they move OH to this side and then they write it as COOH, CH3 dash and OH. That's not what exactly I'm trying to do. The bond is still closed. We are trying to open the bond. We are shifting OH to this direction so that it will come opposite, in the opposite side of the dash bond. So we are basically trying to bring our OH in the opposite side of the dash bond, so that it becomes easier for us to see in which direction your dash is and in which direction your wedge is, and then accordingly you can place it on the vertical line. So this representation is wrong. This movement is also wrong. Now, as I mentioned, horizontal line groups will always be towards the viewer. As I have told you, these are always, the horizontal line means these two are the groups which are towards the viewer in the actual 3D representation, and the vertical line group means that these are away from the viewer. So this information you should be knowing, you should be knowing it properly, so that whenever it comes to convert a Fisher projection to wedge dash, you will be using this information and it will be highly helpful. Okay, now if I rotate my Fisher projection to 180 degree, it doesn't make any change in the configuration of the molecule. The molecule still remains the same, no matter you keep it straight or you rotate it to 180 degree. It's just not going to do anything. I mean, it's not going to change at all. So you have to remember this thing also. If we rotate the Fisher projection by 180 degree, then the configuration doesn't change. Rotation to 90 degree is not allowed. Okay, where and how and why we are going to use it, we will see it later on, but this information you keep in your mind, that when you rotate Fisher projection to 180 degree, it doesn't make any change in the projection, but 90 degree rotation is not allowed. Okay, now let's see a few examples. Now let's see how can we convert the wedge dash representation into the Fisher representation. So here I have taken one example. If you can see here, this is not the, here we have two chiral centers. Okay, so first of all I will draw a line. I will draw a line which will have two chiral centers positions. So basically one cross will be representing one chiral center and another cross will be representing the another chiral center. So here we have hydrogen, chlorine, methyl, hydrogen, chlorine, methyl. Two groups are present over here, right? So what we will do is first of all, what are the groups which are present on normal bond, normal straight bonds? One is methyl and another is this methyl. No matter, it looks like it is there, but it's actually in the normal solid bond. So I'll place these groups on the vertical line. So I've placed these groups on the vertical line. Now what we'll do, now I will move the wedge bond in such a way that it goes into another direction and the bond gets open. Okay, so this representation is a little weird. If I'll open it, it will open it this way. If I'll open it, it will open it this way. Okay, and the molecule will be, I mean, it looks very straight, but it's not as straight. I mean, because this should be actually this way: hydrogen, chlorine. That's how it should have been written. It's my writing error. Okay, when I'll move the chlorine, chlorine will open and go to this side and will open like this. Okay, so you have to basically shift the molecule, shift the wedge to the other side, not crossing the dash but from the other side. So I have moved it to the other side. Okay, and then I have C here, and then again my representation is very poor here. So this is hydrogen, this is chlorine, this is the actual chlorine, and this is my methyl. And now what I have to do, I have to move this to the other side to open it. So when I'll open it, it'll when I'll write it here, it will become quite open like this, and here will be my chlorine. Okay, so now look at the directions of the chlorine. Now, I mean, let me draw the new chlorine like this with a different color. So we will be ignoring this part, we will be ignoring this part, we will see the directions according to this. So now according to this, chlorine is coming on which side? Chlorine is coming on the left side. So I'll write chlorine over here, hydrogen here, here hydrogen is on left, and chlorine is on the right. So this is my Fisher projection. Now let's try out for other questions as well. Very quickly, first two questions I'll explain you, rest you will try it out on your own, and then we will discuss the answer. So first question is CHO here, CH3 here, hydrogen and NH2. First of all, draw the line. This is the chiral center, right CHO, right CH3, and then what we will do, we will move the NH2 here so that bond gets open. So NH2 is now, hydrogen is here and NH2 is here. Done the Fisher projection, right? Let's look at the next compound. Next compound is what? CHO, CH3, hydrogen and NH2. Again, draw a cross. This is the chiral center. Here is my COOH, here is my CH3. And then what we will do, we will just move this NH2 here to open the bond. So here is my NH2 and here is my hydrogen. I'm done with the Fisher projection. Now you try out these questions. Wait, pause the video, try it out on your own, and then check whether your answers are right or wrong. Okay, so I hope you guys would have done it by now. Let's quickly check what should be the answers or what should be the Fisher projection of these molecules. Again, draw the cross and CH2OH and CH3, right? Chlorine will be moved here, so it will be Cl here, fluorine here. Again, let's put a cross over here. Now what we have OH here, we have CH3 here, and what else we have? Oh, I forgot writing a group over here, so let's write it Cl, okay, by mistake probably. I'll move it here. So Cl is here and CH3 is here. Okay, now one thing which you have to look over here is that my CH3 groups are on the uh, I have a CH3 group on my horizontal line, whereas OH on the vertical line. So there is one more saying, or you can say there is one more rule associated with the Fisher projection. It's not rule, it's not a mandatory case, but if you want to form the ideal Fisher projection, in that case you will have to try placing all the carbons, as many carbons as possible, on the vertical line. Okay, so you have to try placing the carbons as many as possible on the vertical lines. But I can see the CH3 is a possible carbon which can be on the vertical line, but it is on the horizontal line. So what can we do to place it? As I mentioned, that 180 rotation of the Fisher projection doesn't make it wrong, at all. I mean, wrong, or it doesn't make it different. It will still remain the same. It will be exactly same configuration. So we are not going to rotate it over here. We do the double switch. So there is a thing called as double switch. If you do double switch or even number of switches in the Fisher projection, the configuration of the molecule doesn't change, or configuration of the Fisher projection doesn't change. So what do we mean by double switch? Let me just show you. So this is the group over here. This is OH, this is CH3, this is chlorine, and this is CH3. This is a right Fisher projection. I'm not saying this is wrong, but we want to get a perfect Fisher projection. So for that, we will try to place all the carbons on the vertical line, and to do that, I will have to do the interchange of the positions of some groups. At least twice the interchange should happen, so that the configuration of molecule doesn't change. It doesn't become a different isomer altogether. So what will I do? One switch is I can switch the position of OH and CH3 with each other. This is one single switch. If I'll do the single switch, the molecule will become CH3, OH, Cl, and CH3. But this is single switch. It's like 90-degree rotation, or the movement in 90-degree, something like that. So this will change the configuration of the molecule. So it will make it a different isomer altogether. So as I mentioned, we can do double switch or the even number of switches to retain the configuration. I have done the one switch right now. This is the first switch. Now what will be the second switch? If I do the switching between OH and CH3, then again it will become the same story, which I don't want. So what we will be doing, we will do the switch between OH and Cl. So we will switch the positions of OH and Cl. This is the second switch. This is second switch. And what will it give me? It will give me CH3, Cl, OH, and CH3. So now I have got the Fisher projection where all the carbons are on the vertical line, where the other groups are on the horizontal line. So basically the perfect Fisher projection without changing the configuration. How configuration has not changed? How do you know about it? You don't know it right now. Right now you don't know about it, but when we learn RNS, I'll come back to the same question and will show you the RNS are the two different isomers of the optical compounds. So we will see the configuration will not change. If this particular compound is R, then after two switches also it will remain R, and if it is S, after two switches it will still remain the S. Okay. So this was an important information. I think I have written this note in the previous slide that you have to try keeping maximum number of carbons in the vertical line, but I had not shown you example there because I wanted to show you with this question. Okay. Now let's move to the next compound. In next compound, again let's put a cross over here, Cn on the top, CH3 at the bottom. Move the OH here. So I have OH here and hydrogen here. I got the Fisher projection. Now let's move to the next set of questions. Try out these questions very quickly and then we will discuss. Now again, in this question, let's have a very quick understanding of this question. I have on the normal bonds, I have CN and I have hydrogen. I have CH3 on the wedge, so I'll move it over here. So I'll get CH3 over here and chlorine over here. But again, the problem which I mentioned, that I want a perfect Fisher projection, so I will make the double switches so that the CH3 can come here and hydrogen can come here. So what I'll do is I'll switch the place between hydrogen and CH3, and then I'll do the other switch like this. So two switches. So basically I'll bring the hydrogen here at the place of CH3 and CH3 at the place of hydrogen. Then I'll switch the positions of hydrogen and chlorine, and in result what you'll get, hydrogen here, chlorine here, CN here, and CH3 here. Okay, so double switch I have done so that I can get the perfect Fisher projection, but I am saying again and again, this is not wrong. But ideally you should be forming, or you should be following all the rules or all the expectations of the Fisher projection. Come to the next compound. I have CN, CH3, H and OH. CN here, CH3 here, OH move it here, and hydrogen. Okay, now look at the next compound. I have two chiral centers here, one is this and one is this. So here I'll be forming it like this. Okay, right? So now I have methyl group here. Oh, my bad, sorry. Methyl on the top and methyl at the bottom. And then again what I'll be doing, I'll be moving CH3, I'll be moving Br here, I'll be moving Br here. So Br, I mean, as I mentioned, this is a very bad drawing. This should have been tilted like this. The dash should be tilted like this, and the upper one dash should have been a little closer to Br. I have written it straight. It's not a right representation. So my hydrogen is on left and my Br is on right. So this is my Fisher projection for this molecule. If you have not got this eighth one, this can be the, I mean, my drawing can be a reason. I'll just correct the drawing. This is how the molecule should have been written, my bad. And then you can try now. I mean, after I change the drawing a bit, you can try this now. Okay, this is methyl. This is how the molecule should have been looking like, and I did a very poor job over here. So this is my Br, this is my hydrogen, and this is methyl. Now you can try solving this and you will get it, what exactly we are talking about. So here we are done with the conversions of Fisher, of wedge and dash to the Fisher projection. Now we are very clear how to make the Fisher projections. Next, in the next class, we'll be talking about R and S configuration of the molecules, because now we know how to draw the Fisher. We can write their configurations, their optical activity is based on what configuration they follow, what kind of isomers they are forming. So we'll be talking about R and S isomers, the rules to determine how a compound can be determined as R, or how the compound can be called as S. And then we'll be talking about the other important terms like enantiomers, diastereomers, and mesomers. So till then, go through it, ask me if you have any doubt in the class. And next class, I mean, we are almost on the verge of completion of the optical isomerism. Once we'll understand what are enantiomers, diastereomers, mesomers, then we'll talk about how to calculate the optical activity in a molecule, basically how to calculate the theta, that we'll do, and after that almost we'll be done with the whole optical isomerism. Bye bye.